Hello everyone. Through this video, I'm going to talk about the current mirror circuit. The current mirror circuits are very important when we design the VLSI circuit. Before go through the current mirror circuit, we need to understand what is the meaning of current mirror circuit. The current mirror circuit is designed to control a current through one active device by controlling the current in the another active device of a circuit, keeping the output current constant regardless of the loading. This is the very important part, keeping the output current constant regardless of loading, which means when we change the load value, it doesn't matter, the reference current controls the current through that load. So here is the simple schematic of the current mirror circuit using two NMOS transistors. So the gate and drain of one NMOS transistor M1 are already connected together, diode connected, and the reference current is also connected to the drain of M1, and the resistor R is also connected to the drain of the M2. IR is the current through that resistor R. Let me explain this operation under the saturation condition of M1 and M2. If you want to understand the meaning of saturation condition, you can go some video where I added at the end of this presentation. So in the saturation region, I can write the reference current, which is equal to the constant, this is kappa, times the aspect ratio times the square of VGS minus VTH, which is equation number 1. Similar to the equation number 1, I can write the current equation for the current through the R, which is IR equal the constant kappa N times WL ratio times the square of VGS minus VTH, which is equation number 2. All parameters have special meanings as I written here. Since the VGS and VTH are same, because this is NMOS transistor, and also the N value is also same because the NMOS transistor, I can get the ratio of equation number 2 and equation number 1. So I am going to divide equation number 2 by equation number 1. Then I will have this equation. The ratio of current equal the fraction of the aspect ratios. So then I can obtain the expression for the IR, which is equal the fraction of aspect ratios times the reference current. So now I can say that I can control IR, either I can change the IREF or I can change the aspect ratios. So this equation independent from the R. This equation independent of the R, which means the R cannot change its current, which is IR. See, if you want to change the current, we need to change the IREF or the W ratios values. So similar to the NMOS transistor, we can also obtain the current mirror expression for the PMOS, which is 100% similar to the NMOS. See, the current through the R, which is IR, equal the fraction of the aspect ratio of M2 and M1 times the reference current. This is 100% same with the NMOS transistors. Now we can talk about the current mirror for the several sub-circuit. Here is the sub-circuit. Actually, here is the current path for the sub-circuit. In here, we have 4 sub-circuits. 1, 2, 3, 4. I can control the current to each sub-circuits only by using IREF and WL ratios. Here, I can get the current through the R naught using this equation. The fraction of WL ratio times the reference current. Similar to this one, here are the other current portions. Only different is the WL ratio. The reference currents will be same for all expressions. By controlling the WL ratios and the reference, we can manage the current. Even when we change the resistors, current through the related resistor will be kept as constant. Now we can run some simulation to confirm the operation of the current mirror. So before do that, first we need to open the LT-SPICE software. As I discussed in my previous video, I already explained how to install, how to simulate, and how to run the simple circuit using the LT-SPICE software. If you have any problem, you can go with that software and you will understand something to run the simulation using the LT-SPICE software. So here, first I need to open the LT-SPICE software. Then I need to open the new schematic window. Under that schematic window, you will see the component list. In that component list, you need to select these special MOSFETs, PMOS4 and NMOS4. After opening that PMOS or NMOS, you can right click on that MOSFET, then you will see this window. In that window, you can change the channel length and channel width. In here, you can type any number you prefer, then okay. So here is the simple schematic. Here is the current mirror circuits that can control three current paths. I already simulated using LT-SPICE software. Here, before simulating, I can get the theoretical value. Here, I have selected the WL ratio 2 micrometer divided by 0.3. In here, 1 micrometer divided by 0.3, 4 micrometer divided by 0.3, 8 micrometer divided by 0.3. So I kept L equal 0.3, which is similar for all NMOS transistors. So only variables is W. Okay. So then I can get the current through the 1K, which is R2, by using this expression, the fraction of the aspect ratio. Okay. The fraction, the W2 divided by W2 divided by L2 means in here is the 1 micro divided by 0.3. Then again, that value should divided by this aspect ratio, which is 2 micro divided by 0.3. So 0.3 and 0.3 will be cancelling out, and then only thing is I need to divide it 10 by 2, then which is 5 microampere. So similar to this process and this method and this technique, I can obtain the current through the R3 and R4, which are 20 microampere and 40 microampere respectively. So in the simulation also, though you will see same values. See, this is the reference value. This is 10 micro, so it is already given into the circuit, and the current value to the R2, which is 5 microampere, and the current to the R3 20 microampere, the current to the R4 40 microampere. So simulation are the theoretical values are same, which means that confirm the operation of the current mirror. Okay, let's simulate together some circuits. Okay, here, as I mentioned, I need to open new schematic window. So here, the new schematic window. So then I need to click the component list. In that component list, so you will see the PMOS. Okay, now let me use PMOS. Okay, here is the PMOS. So I'm going to use 3 PMOS. So here, 3 PMOS, and I need to press Control E to get the mirror image. So then W. So then I can get the wire to connect. So then I need to connect. This is the source. Then I need to connect with all source together. And here is the bulb equal body. So I'm going to connect the bulb with the VDD. So here's the VDD. So let me connect. Okay. So now I'm going to connect the gates according to the structure of the current mirror. The gates are should be connected together. Okay. So I have already connected all gate together. So then this is the reference transistor. For the reference transistor, I need to connect the drain and gate also together. So which is normally called diode connecting. So here I will give the reference current. So let me connect to the wire. Okay, this is just wire. Okay, wire and wire. So now I'm going to connect resistors. So here is the resistor and resistor. Let me go inside the component list to get the current source. So where is the current source? Current. Here is the current source. So here. So current source. So here is the current source. Let me connect the all together. This is the ground. Okay. As you know, the special thing is we need to connect with the ground. Okay. The ground. And finally, I need to apply some voltage. So let me apply that voltage. Okay, done. So now I'm going to give the values. Okay, for the DC voltage source, I'm giving 5. For the current, I am giving maybe 5 micro. Okay, 5 micro. The resistor, see, maybe 2K for each. Okay, doesn't matter. 2K. Okay. Here also 2K. 2K. So now the special thing is the WL ratio here. W. Okay. 300 nano divided by maybe 5 micro. Okay. 5 micro in here. So I'm always keep the L as constant. Okay. So 300 nano, maybe 5, maybe this is 10. Okay. 10 micro in here. Okay. 300 nano and 10 now 20. Okay. And here 30. Okay. 30. 30. So, okay. 30. So now all are set. I just need to run the simulation. Now let me run. Okay. So before run, I need to add some time. So microsecond. So then okay. Okay, it is simulating now. Okay, this one. Okay. So now, so current to the current source, okay, which is see 5 microampere. Now current to the 2K. So here it is 10, okay. This is R1. See, this R1, R1, which is 10 microampere. So it is correct, okay, because the W ratio of the reference one, it is 5 micro divided by 300 nano. Is you can ignore this because I kept this value for all are same. Okay. So then the 5 micro. So inside this one, it is 10 micro. See, 5 divided 10 divided by 5 is 2. 2 multiplied by 5, which is 10. See, same, 100% same. So then I can see the current through the resistor. So R2 resistor. So which is 20 microampere. Why? So if you go inside, this is 20, 20, 20 micro, and here 5 micro. So 20 micro divided by 5, which is 4. Then the 4 times 5 microampere, which is 20 microampere. So then finally you will see the current through the 2K. 2K means the R3 resistor. So something goes wrong, which is 300 nanoampere. Look, let's see. Oh my God. So I just flip the values. Okay. So now L is 230 micro and width is 200. Oh, that is the reason actually. So if you run, then you will get the correct value. Actually, this is correct actually. So now the W is very small. That's why this current become very small. This is nano, okay? That's why this nanoampere. So you will see actually. Then you just need to change this one. This is the, and this is I just kept as 30 micro, okay? So then run. See. Oh, see, now its value is correct. See, this is 30, this is 20, this is 6, this is 10, 20, 30. And the reference 5. It's correct. In the next video, I will simulate little complicated circuit by using the real application of the current mirror. So see you next time.
Here, you can see the body of an NMOS in enhancement mode, the source and drain, the metal oxide gate, and the channel. The first region of operation is the easiest and one that is rarely confused. In an enhancement mode device, this is when there is no voltage on the gate, there is absolutely nothing happening in the channel, and no current can flow. This is called the cutoff region. This is where the depletion region forms beneath the gate and the depletion regions of the PN junction at the source and drain come together. You start to collect charge carriers near the drain at this point, but they don't span across the entire channel. If you put a voltage across the drain and source, you may get a current, but it won't be very large. In saturation, the main factor limiting the current flow is the gate voltage, not the drain source voltage. Most applications of MOSFETs use them in this region, and if the drain source voltage is the same as the gate source voltage, you can assume you're in saturation. Finally, as the gate voltage gets higher than the threshold voltage, electrons from the source and drain flow in and form an inversion layer of electrons that connect the source and drain regions. Now, if you put a voltage across the drain and source, you'll get a current that is linearly related to the voltage. As you increase the drain source voltage, the current will go up. On this graph, we have the drain current, ID, on the y-axis, and the drain source voltage, VDS, on the x-axis. Now, if the gate voltage is 0, as the drain source voltage increases, there will be no current besides a negligible leakage current. But now, assuming we have a gate voltage of 1 volt, as VDS increases, the current will increase linearly until ID gets too big and the amount of current saturates, so that no matter how much more you increase VDS, ID will not get any bigger. If we increase our gate voltage to 2 volts, you can see that you can get a higher VDS with more current flowing before saturating. Comparing the different gate voltages, you can see that greater gate voltages yield a larger ohmic or triode region before ID saturates. But if you look at this graph, moving from left to right, we pass from the triode region to the saturation region. And that's because we're not increasing the gate voltage, we're increasing the drain to source voltage while assuming a set gate voltage acts like a water spigot. The gate voltage is opening the tap, while the drain source voltage is the water pressure. As you open the tap, no water will flow until there is water pressure. And if the tap is open and the water pressure increases, it will increase linearly for a while in the linear mode until no more water is capable of leaving the tap, at which point it will be saturated unless the tap is somehow opened even more. And that's it. We went over the different regions of operation while looking at how the devices operate at the semiconductor level, and also how this translates to how the MOSFET will work in a circuit with different input voltages. Hope you liked the video, subscribe to our channel, and we will catch you in the next one.